All right. Oh, Michelle, I like your background.
Thank you.
I hope that's a background and not actually happening behind you.
No, it's not happening then.
Okay. All right, let's see. What do we got? 1, 2, 3, 4, 5, 6, 7. All right, I'll give it 2 more minutes. We're going to have a short class today. Um, hmm. We got a couple more. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. And we'll see if one more person shows up. Well, I'm recording and I will post this, even though it's going to be just a very short class. So anybody who's not here can listen to the recording. So let's get started. Um, there was just one kind of further new topic I want to just briefly talk about today. It's not much. There's nothing that you need to do or learn. It won't be on the final. And then I was going to give some more details about the final, and then answer questions you had. And I could do a quick review of certain topics that you might feel shaky on if you want, but I was going to leave that up to you and just ask you if there was stuff you wanted me to review or not. Okay, so maybe once I run down the list of topics that are going to be on the final, then you can ask me to review stuff if you want. And I could try to make up examples off the top of my head, or we could pull them out of the book, or we can just look at old web work problems, whatever you want to do. We could just leave this kind of open ended. And then at the end of class, I'll give you instructions on how to actually take the final and when it's going to get posted and when it's going to be due. Got it? All right, so that's the plan. So let's just do it. There's one interesting topic we didn't get to, which I promised I would do, which is the end of chapter 5. So we did all of chapter 5 except for the last section. And then we jumped back to chapter 4, and I just kind of babble about that Monday. I hope you got something out of that, at least enjoyed watching videos of bridges collapse. And then we left off 5.6, and I said after we did chapter 4, we should return to 5.6 and take a look at that. 5.6 is kind of a nice way to tie together everything in chapter 5 with the stuff that we talked about in chapter 4. So I'll share my screen. I'll talk about it a little. I wish I had a document camera so I could just project pages from the book, but I don't. So I'll try to hand draw some of the pictures that are in the book. All right. So this is section 5.6. And I won't talk about this for very long, but I think it makes a nice place to end the class. Hold on, let me rearrange my windows. And there we go. Yeah. It's a nice place to wrap up everything we've done and to end the class and to tie in all the chapters together. It's really focuses on a numerical method. We've done very little with numerical methods. We've just kind of talked about how they work. And tying that together with the work we've done on nonlinear systems, and then the work we did on Monday, just with me talking about non-autonomous systems with a forcing term, like the harmonic oscillators with a forcing term. Um, so um, let's just jump into it. So the example they work through at first is called a periodically forced Duffing equation. So periodically forced Duffing. Oh. Ooh, there's a camera here. Well, I don't even notice that my iPad has a camera. Now I'm curious. Okay, give me 1 minute. Let's see what happens if I do this. Camera, take photo. Can you all see that? Oh, you can. Look at that. I could use my camera to show you stuff. You can all see that, right? Just a page out of the book. Ooh, I have new technology at my disposal. I didn't even know I can do that. Hey, that's awesome. Okay. Of course, my iPad has a camera, but I never even thought to show you pages from the book. I just said, I wish I had a document camera. Of course, I have a document camera. I have an iPad. All right, I'm being stupid. All right, so here's the equations. This is called Duffing's equation. Duffing was a person. I don't know anything about Duffing. My guess is this wasn't discovered terribly long ago, sometime in the, I just had to put a random date on it. I'd say mid 1900s, but it'd be much older. I have no idea. Anyway, here's the equation. It's really a system of equations. Actually, it's a system of equations as presented in the book, but it looks to me like it's just somebody took a single second order equation and split it up into a system of two. Yeah, that looks like it just came from breaking up a single second order equation to a pair of first order equations, right? Because you got that dy dt equals v, so somebody sets the velocity term equal to dy dt. Or sorry, set the dy dt term, which is the velocity term, equal to this new variable v. Okay, so this is a Hamiltonian system. They don't ever say that in the book. Oh, they do say it. This is a Hamiltonian system. They say the Hamiltonian energy h of y v is v squared over 2 minus y squared over 2 plus y to the 4th over 4. So we could plot that on a three-dimensional graphing program like I've shared with you, and then look at the level curves of that to get the phase plane. Or we could just do the usual stuff, find the equilibrium points, linear, just ignore the fact that it's Hamiltonian, find the equilibrium points. And if we did that, we would find 3 equilibrium points on the x-axis, sorry, on the v-axis. So this is y, v. And this equilibrium point will be a center. And so would this one. And the center equilibrium point is a saddle. Okay. Now that's all kind of consistent with the fact that it's Hamiltonian. So one thing to remember about Hamiltonian systems is that you only have 2 choices for equilibrium points, which are centers and saddles. And actually just knowing that it's Hamiltonian, not even knowing the function here, you just ignore that function. The fact that it's Hamiltonian means that all of the trajectories of all the orbits have to be things you'd see as if they were level curves, right? So you would never see, for example, if we had kind of a spiral sink, you would never see that as the level curve for a three-dimensional function. Imagine plotting a graph in 3 dimensions. You have the surface in 3 dimensions. Looking at these horizontal slices, you're only going to see, like, around a maximum minimal, you'll just see circles, simple closed curves. Okay, you'll never see something like one of these spirals. Okay, so you can, again, if we do all the work of linearizing around each, we'd see these nice eigenspaces around the saddle. We'd see these nice circles around the center tangency and things, the directions. You could even plot the directions out, in, and that tells you the directions on these circles to be consistent. You have to go like this. And this actually loops around, and then you get these bigger things here. All right, fine. Okay, that's all just a review. So we have this, we had some first order equation that got converted before we even got to it to a we had a second order equation that got converted to a first order system. A first order system is Hamiltonian, so we know something about its trajectories, and then we could do the work to actually plot it, either by finding the Hamiltonian function, graphing it, and then finding the level sets, or by actually doing the work to linearize around each equilibrium point and just drawing the picture from that, okay? All right, now the thing that we're gonna add to all of this is a forcing term. So this is, again, just like what we did on Monday, where we had the mass on a spring, and then we added this extra term to represent energy being put into the system. And when it got really interesting, when we started talking about resonance, was when that forcing term was periodic. So we just kind of add energy and then take away energy, and then add energy and then take away energy. Right? So it's represented, all kinds of physical systems have energy being applied periodically. So the forcing term we're going to add here is epsilon times sine of t. So that epsilon is just a variable, it's a parameter, right? That's the technical term, that allows us to explore this system with different values of epsilon. So this isn't just one system, it's an infinite number of different systems depending on the value of epsilon that we pick. So we can explore the behavior of this system when epsilon is 0.1. We can explore the behavior of the system when epsilon is 10, okay? And the thing is, we can't draw the phase portrait anymore. All of this stuff just kind of disappears, it goes away. But you would expect when epsilon is very, very small that we would get a picture somehow that's kind of like this. So the right way to draw a system, the problem is now, so again, in your mind, pretend epsilon there is a constant, in which case the only variables on the page here are y, v, and t, which means the trajectories, the solution curves, are going to be plotted on a set of axes where you have a y-axis, a v-axis, and a t-axis. Okay, so the right way to do that, I'll try to draw it. And again, maybe I'll turn on the camera and show you pictures from the book now. Imagine you have kind of this cube in space, and you have the v and y-axis, v and y-axis. But then you also have this t direction going through the cube. That's the t direction. The v direction is up, the y direction is to the right, and the t direction is going into the page there. And what we'll see before we had the t term, we had the y-v plane and we had an initial condition, and then you say, okay, what happens to this initial condition? It starts moving around and does stuff. Right? We'll have the same thing now, but now we're in 3 dimensions. So we have some initial condition in this plane where t equals 0, and then that point will move, but it moves, and the way it moves is not only determined by y and v, but also by t. So the solution curves kind of march through this system and end up just keeping going. And we can extend this box for as long as we want, depending on how long of a time range we look at. Now, the insight, the only real content of this section 5.6 is the observation that the forcing term here is periodic, which means we have the same exact system when t equals 0 as we do when t equals 2 pi, and it's the same system when t equals 4 pi, and when t equals 6 pi, we get the exact same system in every case. So just like any differential equation, the fate of any point just depends on its initial conditions. So if I pick an initial condition in this picture, then the trajectory only depends on what that initial condition was, right? And the observation that it's periodic means I can only draw a chunk of this picture between 0 and 2 pi. So here, this is where t equals 0, and on the back plane here, the back plane, that's where t equals 2 pi. And the point is that the fate of a particular point depends on y, v, and t, okay? And all these equations that relate y, v, and t from our system. But those equations are the same when t equals 0 as they are when t equals 2 pi. So said a different way, if I start with some initial condition here where t equals 0, and I say, okay, now what happens to that point? Well, it's going to kind of march through space and do stuff and land over here at some point where t equals 2 pi. Okay? Now, at that point at the end, there's some particular value of y, there's some particular value of v, and I'm at t equals 2 pi. But as far as the system is concerned, that's the exact same thing as if I project this back onto the original plane, look at the same value of y, the same value of v, but now I look at t equals 0, right? Everything where t equals 2 pi is behaving the same as where t equals 0. And now I say, okay, what happens to the point now? Oh, I don't know. It's going to just sort of march through this box and end up somewhere else, okay? And now I can project that point back to the first face, and I end up over here. And I say, okay, what happens to that point? Well, now I will just wait, kind of march through the system, and now maybe it ends up over here. Okay, so do you see what's happening is that rather than thinking of this entire system in this y direction, v direction, in this infinitely long t direction, we're just looking at a chunk of space where we have an infinite y direction and an infinite v direction, but the t direction only goes from 0 to 2 pi. And we're thinking of solution curves as kind of wrapping around that little chunk of space, because the system is the same where t equals 2 pi as it is where t equals 0. Now, the reason why we're doing all this is because this picture gets very complicated. And as in most of this class, we're trying to develop geometric and visual tools to understand the behavior of these differential equations. But if I try to plot this picture in three-dimensional space, it's very, very quickly going to get very complicated. Even just plotting one trajectory as it winds through this box a couple of times, I'm going to get this kind of big, messy tangle. It's just going to look like somebody's hair, just all tangled up from beginning to end. Okay. So instead of doing that, we'll just plot this first plane and all these points that we get every time we march through the box. So if I just look at that first plane there, where t equals 0, but this is also where t equals 2 pi and t equals 4 pi, etc. And I start with some initial condition. Now I wait some amount of time. So I started with some initial condition, right? That's this one right here. Now I wait some amount of time, it winds through the box, and now I get to some new point, okay? So now I get to some new point over here. And then I wait some amount of time and it winds through the box, and then I get to some other point, which is here. And then I wait some amount of time and I get to some point that's here, and then here, and then here, and then here, and then here. And sometimes when you do this with a computer and you let the computer just kind of fill in the picture, even though the points look like they're hopping around randomly around this plane, sometimes you can start to see some structure emerge. Like maybe all the points you get lie in a circle, like this. So it's a way to start seeing some structure out of something that looks completely chaotic. If we look at this picture, we'll just see this tangle of strings all kind of knotted together, and it won't be very insightful at all. But when we look at this picture down here, then suddenly like some structure emerges. We start to understand, oh, things can't go off in the y direction infinitely. They're just constrained to this circle. There's a lot of qualitative information here in this picture. And this is called the Poincare return map. Henri Poincare is a French mathematician. He did a lot of his work right around the year 1900, both before and after the year 1900. I think he died, I want to say, shortly after 1900, so late 1800s or so. And he studied these kinds of systems, differential equations that had already been around for a while. And he was the one who is responsible for this way of thinking about it. And if you just consider the fact that he was doing that before computers were around, that's kind of amazing, right? He was thinking that these kinds of pictures should exist and already doing some primitive plots of these kinds of pictures without the aid of computers. That's kind of amazing. Now that we have computers, we can just instantly program something where we get these amazing pictures right off the bat. And in this case, the pictures we get are often very, very closely related to the original system. So especially for small values of epsilon. So for example, here's the original system. I'll draw it in black. We had these 3 equilibrium points, and we had these loops, and we have these curves right here. Right? And one of the things the book points out is if we look at now this modified system where we add this forcing term, but we use a really small value of epsilon, like epsilon equals 0.06 is the one they use. So I'm going to switch colors. So kind of superimpose what happens when you add epsilon equals 0.06. You add this term. And now we do something different. The picture's going to change. It's not this picture anymore, but I'm going to superimpose the new picture on the old picture. So now if I start with some initial condition, in the old picture, it would have just circled around that center and just kind of gone smoothly around. And in the new picture, it does something similar. It doesn't exactly follow that curve, but it's pretty close to it. It's going to jump around it, the return map. And it's going to follow this curve. So you can see that the forcing term, it does make things jump around kind of seemingly randomly, but this randomness, once you draw enough of it, it stops looking so random, and it starts looking a lot like with a small forcing term without much surprise. A small forcing term will give you a picture that's close to the original picture, but you have to draw the picture correctly. The way to draw the picture is to use this idea of the Poincare return map and just draw these slices in time at 0, 2 pi, 4 pi, 6 pi, right? And then you start to see the same picture if you do that. So, we're tying everything together here. We've got a nonlinear system. It's Hamiltonian, right? So that's all chapter 5 stuff, right? We can linearize, we can look at null lines, we can do all that. It's Hamiltonian, so we can look at level sets, right? And then we can jump back into chapter 4 and add a periodic forcing term. And the whole point of section 5.6 is to kind of reconcile all that. And this Poincare return map is the way to do that, is to just draw these slices in time at different periodic time intervals. And the pictures you get look similar. They don't always look so similar. As you might expect, as you increase epsilon to something bigger, and they have a beautiful picture of this, and I'll show you the picture, even at something like 0.06, so going from, same value of epsilon, but a bigger initial condition, different initial condition. We can get pictures that look kind of spectacular. And you know what, I might as well, instead of trying to redraw this, I'll just do it. I'll just use my camera here to show you what we can get. Camera. Black. There we go. Okay, hopefully you all are seeing that, right? So there's the Poincare return map they're showing. That's without any forcing at all. Okay, that's with no forcing term whatsoever. If we add a forcing term, then you see a particular solution curve for the initial condition, for an initial condition very close to 1, 0. If we look at an initial condition that's further away, it's on the next page, it's looking a little more random, but you can still see some of the structure of that initial picture, right? It's not completely random. I mean, some of that structure is still preserved, which is kind of amazing, right? That these dots, even though it looks like a random cloud, it's not random. There's still a lot of qualitative information there that you can extract from this kind of picture. Okay. If you look at the graphs of y and t independently, you can see that they move kind of oscillate above that horizontal axis and below that horizontal axis. And one of the things that we're seeing here is that points with a very similar initial condition do eventually diverge from each other, and then the behavior after some time is completely unrelated. And we saw that happening when we looked at the Lorentz attractor when we were working in section 5.5 at the end of last week, last Wednesday. And that was this phenomenon called sensitive dependence on initial conditions, which is the mathematician's technical term for the popular word chaos. So this is another example of a chaotic system. Chaos essentially means it's completely unpredictable, but that doesn't mean it's without structure. So a lot of people confuse the word chaos with the word random. And chaos doesn't mean random. It means unpredictable, but random means there's no patterns that emerge. And you can see with this system, there are patterns. It's not totally random. You can't just get any point in the plane when you start with a given initial condition. There is definite structure here, but the location of each point is unpredictable. There's no way to do long-term prediction, even with a computer, because computers have a finite amount of precision. And even if your computer is accurate to 32 decimal places, then there's still some error that happens. And that's exactly what this picture is indicating, is that no matter how small the error, eventually you're going to be off from the actual reality of what will happen. If two trajectories diverge even a tiny bit, then eventually they will diverge a lot. And computer precision is a real impediment to that because we don't have infinite precision computers. Okay, that's about all there is to section 5.6. They go to another example after that, which is going back to the forced pendulum. So the pendulum. So you have a simple pendulum that's just oscillating back and forth. But now again, we add a periodic forcing term. So without that epsilon term, that's the equation we had analyzed for the pendulum. And remember, we got these solutions that look like either just the pendulum moving back and forth, or if you give it enough of an initial kick, then it just spins around and spins around and spins around. There's some interesting modeling going on there. Now we're going to add a periodic kick to it, this epsilon sine t term, and it oscillates periodically. And again, as you would expect now, this periodically forced system now has chaotic behavior. So if you look at a pendulum with a periodic forcing term that's periodically applying a kick to the pendulum, then the motion of that pendulum won't just go back and forth. Sometimes it'll jump over the hump, sometimes it'll just oscillate, and then it'll get enough of a kick to go over the hump again, and it'll just keep going back, and then sometimes it'll go back the other way. And it's got some amazing dynamics there. But again, if you go through the Poincare return map, you still get a lot of interesting structure there. Even though you get behavior that's seemingly random, there's still some structure to that behavior. And you can see that when you do the Poincare return map. Here it is. Here's the Poincare map for the forced pendulum. Even with epsilon is 0.01 for a tiny amount of forcing, you still get something that's seemingly random. But yet there is still some structure there that you can kind of make out. I'll do one more thing, just show you one more thing, and then I'll just stop talking and we'll end the class there. Let's see, so let me stop sharing that screen. And one more quick thing, which is looking at the double pendulum is an interesting example. It's not in chapter 5. I think it is in chapter, I want to say the last chapter, chapter 8, talks a little bit about the double pendulum. But it's interesting to see the forced pendulum acts a lot like a double pendulum. And there is an interesting animation of that that's easy to find. If any of you have had CS5, you did some programming in GlowScript, and somebody wrote a GlowScript program to simulate the double pendulum. So double pendulum is just a pendulum hanging from a pendulum. And again, it's another example where it's this variation on the pendulum that mimics that where you see this chaotic behavior. Everybody see that? If you just watch it, the equations around a double pendulum are pretty simple. And you can see sometimes, even if you just focus on the red bar, sometimes that red bar will go all the way over, sometimes it won't. And the green bar certainly is doing some really crazy things. And there are some desk toys that, you'll see office executives have, where it's just a simple double pendulum, and you give it a little kick, and it just starts oscillating totally chaotically. And it's kind of fascinating to watch this thing in real life, to watch a real one. It's probably, I haven't, always dangerous to go off script, but let's do it. Let's go to YouTube, see if somebody's just filmed an actual double pendulum, so you can see. It's a little more satisfying to see it in real life. Yeah, here we go. Looks like somebody's science classroom. That's not very exciting. Oh, now I see that was a single pendulum. Now he's going to loosen up that hinge so that the two ends could oscillate wildly. And you see now the behavior gets completely chaotic. And this is without any forcing at all. So it will eventually, the friction will just make it wind down. Presumably it's been designed to minimize friction. Those are probably ball bearing joints that have very, very little friction. But it's totally chaotic and random seeming. But if you were to plot the return map for this, then you would probably start to see some structure emerging here. It's kind of interesting. So all the stuff we're doing all semester on differential equations, it's really behind a whole lot of natural phenomena. And I think really thinking about the work that we've done this semester can help you understand the world. We saw ties last time to music theory, to engineering, all kinds of interesting applications here that help you really understand some of the things you're seeing. It's kind of dying down now. You see friction is just taking over. So the oscillations are getting smaller and smaller, but they're still wildly unpredictable. All right, that's as good a place as any to end this class officially. That's the last kind of new material I'll say. If you're interested, I do encourage you to read that section of the book. Although even in that section of the book, everything is done numerically. So they had a computer generating all the pictures in that section of the book. Let me stop this on my other screen. Any questions about that stuff before I start talking about the final reviewing? No? All right, cool, good. Yay, I hope you enjoyed all that. Couple of things. Course evaluations. Course evaluations this semester are being done electronically. So at some point in the next couple of days, you will receive a link and you'll be asked to go online and fill out things electronically. I think through Sakai or through the portal, if I'm not, I don't know which one. So you've probably already done it for some of your other classes. Is it done through Sakai or the portal? I don't remember. Probably Sakai. So look out for an email from one of those that says course evals for this class, and it'll be a quick electronic online survey that you'll fill out. The final exam I will release today. I initially said I'd just release it today and give you a week to do it, but that is kind of overkill. I thought afterwards that's really way too much time that I should be giving you for our final. So our official final for this class would be Tuesday at 9 a.m. So that's, it would go from 9 to 12. So I'm going to make the due date for the final. Let's work backwards. The due date for the final will be the end of our normal final exam time. So you need to get the final back to me by noon on Tuesday, okay? And I will release it. I know you've got other stuff going on in finals week. I hate to release it today because that's too much time. So let's say I'll release it Friday. Is that fair? So you have the weekend to do it and get it back to me. Okay, so Friday, look for it Friday. I don't know, look for it Friday around noon. So I'll give you from noon Friday to noon Tuesday. How does that sound? Reasonable? Okay. The way I will release the final is through the Sakai tab. For this class, you will go to assignments. And I've never posted any assignments for this class on Sakai. I've done it for other classes. So when you go to the assignments tab on Sakai, and I'll send an email out to the class saying all this, so you should see that as well. But you'll go to the assignments tab for this class on Sakai. There'll be a single assignment listed, and the assignment will say Math 102 Final Exam. You'll click on that, and there'll be a link to a PDF that you can download, which will have just a PDF of the final exam, which should be the question sheet. You'll fill it out on your own paper, and then you need to scan that. So if you don't have access to a scanner, you can use your phone. I prefer PDF is easier. If you want to just take regular photos, that's probably fine. But there's plenty of apps for any kind of phone platform where you can use your phone to scan pictures into a PDF. I use on my iPhone, I use an app called TurboScan that I've been using for years. It's been around a long time, and it does a good job. So, but I'm not going to endorse any one particular program. So just somehow scan it into a PDF preferably. And then when you go back to that same assignments tab where it says, where you downloaded the PDF, there will be a place there for you to upload your scanned final exam. Okay, it should be pretty obvious. So there'll be a download link, and also there'll be an upload window where you'll find that file, you'll navigate to that file on your computer, and then just click upload, and it'll upload it to me. Okay, and I will set a deadline. It will have to be uploaded by noon on Tuesday, or that link will shut down. Okay, so don't be late. Make sure you get it in by noon on Tuesday, or you won't be able to submit it to me. If you have trouble, you can always email me and say, hey, I missed the deadline by 1 minute. And if it's something like that, you can email it to me. But I'd rather just coordinate this all through Sakai. So just get it to me by noon on Tuesday. I think that's totally reasonable. Got any questions on just the mechanics of the exam, how that's going to work? Go to Sakai, go to the assignments tab, download the PDF. When you're done, scan your answers, upload it. Easy enough?
My Wi-Fi quit out in the beginning of that. Is that pretty much everything you said during this portion? You haven't talked about content or questions or anything?
Correct. Yep.
Okay, cool.
Yep.
Thank you.
Yep. Okay, content. It's mostly, I will say, the work we've done all semester has been cumulative, which means everything's built on everything else we've ever done. And I love classes like that. I hate classes that kind of jump around. Like I hate teaching Calc 2 because it just jumps around. And the stuff you do at the end of Calc 2 has nothing to do with the stuff you do at the beginning of Calc 2. This class I like because it does build and build and build and build, which means I only really need to test you on the stuff at the end, and it's a comprehensive exam. It really is testing you on everything we did all semester. So I'll tell you right now, there are only 2 questions on the exam, but the questions have lots of parts. And one of those questions, you'll see this on Friday when you see it. One of those questions is just, I'm going to give you a nonlinear system, and I'm going to ask you to do everything we learned to do with nonlinear systems. So you'll have to solve for the equilibrium points, linearize around each equilibrium point. Then, you'll have to find the eigenvalues, eigenvectors around each equilibrium point, identify if they're saddles, sinks, spiral sources, etc., blah, 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 blah. Okay, and then plot all that on a single phase plane. Add to your picture the nullclines, another section from chapter 5. And then all of that information, the equilibrium points, the linearization around equilibrium points, etc., together with the nullclines, should help you draw the entire phase plane, even away from the equilibrium point. So I'll have enough information to draw everything there. Then I'll give you an initial condition, just ask you to sketch in on the phase plane what happens with that initial condition. And then I'll ask you to just draw the graph of x versus t and y versus t for that given initial condition. Okay, so it's pretty comprehensive. It really covers, really kind of retroactively will cover all the material in chapter 3 and even earlier, and all the material in chapter 5 at the same time. The only thing that doesn't cover is the stuff on Hamiltonian and dissipative systems. So the second question on the exam will focus more on that. So you'll either have a Hamiltonian or a dissipative system. I'll just give you one of those, but I'm not telling you which. You should study both between now and Friday. And I might ask if it's Hamiltonian, I might ask you to find the Hamiltonian function. Even if it's dissipative, it's harder to find the Lyapunov function. So I might give you the Lyapunov function and ask you to confirm that it's a dissipative system, something like that. We did some work on gradient systems as well. So the dissipative system might just be a gradient system, which was a special case. And in that case, it is much easier to find the Lyapunov function. And then, again, use all that information. So again, you'll be asked to sketch the phase plane, but now you're going to use the fact that it's dissipative or Hamiltonian and how that affects the picture of your phase portrait. So again, you'll probably still have to find the equilibrium points and linearize around the equilibrium points. But if you bring in the fact that it's dissipative or Hamiltonian, that'll also help you draw the picture in that case. Okay, and then again, I'll give you an initial condition and ask you to find the solution curve for that initial condition once you have the phase plane. Should tie it all together. And that's kind of everything we've done. It's really will cover chapter 5 pretty well. And then, the fact that you have to linearize around the equilibrium points and analyze those linear systems kind of retroactively means it also covers all the material in chapter 3 as well, too. That's it. That's going to be the whole exam. Any questions on that or anything you want me to review? I'm happy to kind of go over anything we've talked about at any point in the semester. At this point, it's our last day. This is your last chance to ask me questions. I'm not going to answer questions about the exam during my office hours. That wouldn't be fair to people who don't come to my office hours. If you have a clarifying question, like I don't understand if question 3 is asking me about X or T, I don't know, something technical like that, you can always shoot me a quick email and I'll answer short little questions like that just to clarify what the questions are asking.
In terms of when we're, oh, sorry.
Yeah, go ahead.
When we're graphing, when we're doing all the phase portraits for the entire system and then doing the separate ones for like an initial condition, can we do them on separate graphs just because those pictures can get very busy?
Yep.
Okay.
Yep. I mean, you may or may not want to. Here, I'll share my screen again. My iPad screen. Just clarify, what I mean by any of that. Share screen. Boy, that's kind of frustrating. On the last class day, I realized I could use the camera on my iPad. I guess that was stupid. All right. So again, I'm going to give you some kind of system. Oops, stop that. dx dt equals something. dy dt. Yeah, sorry about my handwriting. Equals something. You're going to find the equilibrium points, right? You're going to set these equal to 0, and you're going to find some solutions. X comma y equals. You'll get some pairs of points. You'll get some list of equilibrium points. You'll have to linearize around equilibrium points. You'll have to draw the null lines. And then you have to put that together in a phase plane. So maybe you'll get one equilibrium point that's over here, and another one over here, and another one over here. And you'll find, oh, this first one is a saddle. And you'll find the eigenvectors. That'll give you these lines, the eigenspaces. And based on the eigenvalues, you'll know which ones point in and which ones point out. Maybe you'll find one of them is a center. And from some of the other information in the picture, you might be able to determine which way those curves go. You should be able to figure out how those curves go, left or right. Maybe you'll find a spiral source or something over here, etc. And then maybe on top of this, you'll be able to plot I will ask you to plot the null lines. So this isn't going to be accurate here, but remember the null lines were these curves in this picture where you have your vectors. One of the null lines was the x null line, where you've set dy dt equal to 0, which means all of your vectors are horizontal or vertical. And if you set, so horizontal, and if you set dx dt equal to 0, you get the y null-cline where all your vectors are vertical. Right? So those are the null-clines. And then knowing all that now, maybe you can fill in the whole picture. And then on top of that, I'll give you some initial condition, maybe over here, and you might find, oh, with that initial condition, given all the direct pictures and everything else, now you look like, I don't know, you look like this, or this, or this. I don't know. I'm just drawing something kind of random here, right? You've got to draw something that kind of follows the vector field. And then once you know that, right, what we're really drawing here are the x-axis and the y-axis. But t is hidden from this. We've done this before. I've asked you this on previous exams. At this point now, I can say, okay, here's x versus time and y versus time. And I give you some initial condition. So that's this point right here. And it's got some x coordinate and some y coordinate. And based on the picture that you're going to get here, you should be able to reason through what's happening over here. Maybe it goes up and oscillates, and maybe it levels off to some asymptote or something like that. And maybe this just goes and then goes down to 0. We've seen all kinds of pictures like this throughout the semester where you can kind of reason through what's going on. None of this should look too foreign to you, right? I'm just asking you to do it all, put it all together in one problem. Good? Robert, does that clarify
Yes.
things?
Yes, thank you.
Yeah. So you probably do want to sketch, a lot of stuff together on one picture. But then when you do x of t and y of t, you do want those separate. Yeah. Good. Other questions? Anything you want me to review? You've got the book. It's open book. So, if I ask you a question on Hamiltonian functions, you've got the book. You could always go reread the chapter on Hamiltonian functions if you have no idea what I'm asking you or how to do it. All right. Well, if that's it, we'll just call it. And again, look out around noon on Friday. I'll release the exam on Sakai, and it'll be due noon on Tuesday. Good? All right. It's been a pleasure having you all.
Thank
summer.
you.
Thank you.
Too.
Professor.
Yeah. Bye.